We've seen that complex numbers were all about rotation, but so far we've only been able to move in some kind of non-continuous spiraling path, like this one, through complex multiplication. Now the question is, starting from this point, is there a way to get to the exact opposite, over here, following a perfect continuous circular path? Is there a way? Is there a way to do this only by using complex multiplication? So let's try some things out and see what happens. The starting position of our particle J will be right here on the complex plane. J1. So this is also the complex number 1 plus 0i. What we want to do is make this particle move in a continuous circular path, so that its final position is at the exact opposite of the starting position. We want to accomplish this through complex multiplication. Let's try multiplying the particle by the complex number 1 plus 0.5i. Obviously this will be equal to 1 plus 0.5i. So now the particle will sit somewhere around here. So this will be J2, position 2 of the particle. Let's multiply it again by 1 plus 0.5i. So 1 times 1 plus 0.5i squared. So this will be equal to 0.75 plus I. So now the particle will sit somewhere around here. So this will be J3. Again, if we multiply it once more by 1 plus 0.5i, so we get 1 plus 0.5i to the power of 3. So this will be equal to 0.25 plus 1.4i. So now the particle will sit somewhere around here, position 4. So let's continue. 1 times 1 plus 0.5 I to the 4th power will be approximately equal to minus 0.4 plus 1.5 I. So now the particle will sit somewhere around here. J5, position 5. So let's do it one last time. 1 times 1 plus 0.5 I to the power of 5, so it is approximately equal to minus 1.2 plus 1.3 I. So now the particle will sit somewhere around here. Position 6. If we start drawing the modulus of those points, we can immediately see that we are still getting this non-continuous spiraling path. We are still not able to get the continuous circular path that we are looking for. But maybe by using a complex number whose argument and modulus is smaller, maybe we'll be able to do just that. So let's repeat the same process. Only this time we'll be using the complex number 1 plus 0.25i. So 1 times 1 plus 0.25i will be obviously equal to 1 plus 0.25i. So the particle will sit somewhere around here. So this will be position 2. So if we do this again, 1 times 1 plus 0.25i squared, this will be approximately equal to 0.94 plus 0.5i. So the particle will now sit somewhere around here, J3. So by repeating the process over and over again, we would get that the position 4 of the particle should be somewhere around here, J4. The position 5 somewhere around here, J5. And the position 6 somewhere around here. Now if we draw the modulus of those points, we can see that we are still getting this spiraling path, and we are still not continuous. But because there is less scaling up going on, we are getting a trajectory which looks a bit more like the one we are looking for. So in both cases, the particle is pushed a little further away every time we perform the multiplication. Also, the particle will occupy only a given number of positions. These are not continuous trajectories. What we would need is to find a complex number, such that the scaling up is infinitely small. Let's focus on a very special complex number. Z is equal to 1 plus pi I over n, where n is a whole number that we choose. If we were to represent z on a complex plane, it would look something like this. So maybe z would be somewhere over here. So its modulus would be this distance, modulus z. It would have an imaginary part of pi I over n, and a real part of 1. And its argument will be this angle over here. We would call it theta. Let's focus on the modulus and the argument of z. Using a little bit of trigonometry, we can see that the tangent of theta is equal to pi over n, opposite over adjacent. So the argument of z, which is equal to theta, is equal to the arctangent of pi over n. Now, by using the Pythagorean theorem, we can tell that the modulus of z is equal to the square root of 1 plus pi squared over n squared. So let's keep this aside for a moment. Let's first rewrite our complex number z in trigonometric form. So we get z is equal to the modulus of z times the cosine of theta plus I times sine of theta. Now, what we will do is multiply our particle j by z the same way we did previously, except that this time we are not going to multiply z by itself 5 times, like we did for 1 plus 1 half I or 1 plus 1/4 phi. No, we are going to do it n times. So let's see what happens. So j times z taken to the power of n. So remember that j is equal to 1, This is the starting position of our particle. So this would be equal to the modulus of z times cosine of theta plus I times sine of theta taken to the power of n. So we can simplify this relationship using the De Moivre formula. So De Moivre formula states that the cosine of x plus I times sine of x taken to the power of n is equal to cosine of nx plus I times sine of nx. So using this formula we get that j times z taken to the n power is equal to the modulus of z taken to the n power times cosine of n theta plus I times sine of n theta. Now we can replace the modulus of z and theta using what we found a minute ago. So we found that theta is equal to the arctan of pi over n, and that the modulus of z is equal to the square root of 1 plus pi squared over n squared. So we can use that to get that j times z to the n power is equal to the square root of 1 plus pi squared over n squared, all of that taken to the n power, times the cosine of n times the arctan of pi over n plus I times sine of n times arctan of pi over n. But we still did not choose any value for n. So let's choose a very special one. Let's see what happens as n goes towards infinity. Let's take the limit as n goes to infinity of this whole thing. Limit as n goes to infinity. So in order to solve this, we can start with the limit as n goes to infinity of this term over here. So if n goes to infinity, this term will go to 0. So this will go towards 1. So square root of 1 is equal to 1, no matter what n is. So this whole thing is going to be equal to 1 as n goes to infinity. Now to solve this part, we first need to know that the limit as n goes to infinity of n times the arctangent of pi over n is actually equal to pi. So we get that the limit as n goes to infinity of j times z taken to the power of n is equal to the cosine of pi plus I times the sine of pi. So the limit as n goes to infinity of 1 plus pi I divided by n to the n power, so this is z to the n power. This is equal to cosine of pi, so minus 1 plus I times the sine of pi. So sine of pi is equal to 0, so we get minus 1 plus 0. Minus 1. So that is quite amazing, because our particle started right here at the beginning, position 1. But after this infinite complex multiplication, the particle ended up exactly where we wanted, at the exact opposite. What happened is that n was so big, so close to infinity, that the scaling up was infinitely small. Not like in the first cases that we've seen, where every time we multiplied, the particle was pushed a little further away from the origin. This time, the particle was not pushed away at all. She stayed at the same distance away from the origin. But let me show you exactly what happened for different values of n. So this is what happened for different values of n. Here for n equals 6, well, you can see that we've got a lot of scaling up going on here, and we are still getting this non-continuous spiraling path. But as n increases towards infinity, here we've got n equals 512, we are getting closer and closer to this continuous circular path. So it was definitely possible to make our particle move in a perfect circular trajectory, and we did it through an infinite complex multiplication. But now let me go back to the relationship we found. We can rewrite this relationship as the limit as n goes to infinity of 1 plus 1 over n to the n power, and all of this to the I pi power, so equal minus 1. But if you remember the definition of the number e is equal as the limit as n goes to infinity of 1 plus 1 over n to the n power. So what we can say is actually that e to the I pi is equal to minus 1, or that e to the I pi plus 1 equals 0. This is the Euler's identity, and now we know what it means visually. It means that we can move in a perfect circle through an infinite complex multiplication.